Hey, Calc folks. So just a reminder where we're at. We've spent a lot of time learning how to take derivatives to differentiate. Okay, and in our last little unit, we focused on one application of derivatives called related rates. Well, we're going to continue to study as to how derivatives help us do things, find things, solve things. And what we're going to be starting to look at today are finding extrema of functions. And I'm excited for this. This is really going to get into how derivatives help us determine what functions look like in any type of function. By the end of our unit here, before we get to our next test, you're going to become the best at sketching a curve of any function as you've ever been, right? And we've done a lot of graphing over our time together in different courses. But man, you are going to be so good at knowing what a function looks like. I can give you any function, okay, and you are going to be able to draw the best graphs of your life. All right. Okay. But we're going to focus today just on finding extrema. Now, just a review here on what extrema are. Extrema would be a maximum or a minimum. Okay. And there's different types. There's local or relative, or there's global or absolute, different words that we use there. So just a little reminder here. So if we have a function that looks like this, what does this have for extrema? Well, I notice right here that this point is lower than every point around it. Okay, so it's a minimum. However, is it the minimum on the entire graph here? No, the minimum on the entire graph is right here. So this is called a local or relative minimum, where this is a global or absolute minimum. Okay, so I use global, absolute, local, relative. I'll use those at different times. It's just depending on who you talk to, the book that you're taking a look at, they might use one word versus the other. So just be flexible with that. All right, so local minimum, global minimum, relative min, absolute min. All right. How about a maximum? Well, I see this is higher than every point around it, and so is this one. However, this is the highest point on the graph, so this is the global or absolute maximum, and this is a local or relative maximum. All right. Okay. Now, we're going to get into a theorem right away here. Okay, the extreme value theorem says if f is continuous on a closed interval AB. Okay, stop. We got to remember, what does that mean? What does it mean to be a continuous function? What does it mean to be on a closed interval? Well, closed interval, okay, let me just pick an A. There's A. Let's say B is right here. Closed interval means we have endpoints, right? The closed dots, endpoints, not open dots. Okay. Continuous, okay, we know that it can be drawn without lifting the pencil. It's a nice, smooth, continuous curve. So it says if f, and let me just draw a function that meets that criteria. All right, closed interval, continuous function. If f is continuous on a closed interval AB, then f has a minimum and a maximum on the interval. Does this have a minimum? Yes. Where? Right here. Okay. It is the absolute minimum. Okay. It also has a local or a relative minimum right there. Does it have a maximum? Yep. Okay. Its maximum is probably right about there, its highest point. So what the extreme value theorem says is this is true for any function that's continuous on a closed interval. So let me try drawing another one. How about if I draw something that looks like this? Okay. Does this have both a minimum and a maximum? Yep. It has two maximums. Okay, two maxima, and it has one minimum. Okay. How about that? Yep. Minimum there, maximum there. How about? How about that? Okay, trying to draw that horizontally. Actually, and every point on this one is a maximum. Every point is also the minimum. So lots of options there. Hey, let's take a look at some more functions that I've drawn. Okay, let's identify the extrema. Not my best sketches in the world, but we'll go with this. Notice there's open dots here. Okay, so this does not meet the criteria of the extreme value theorem, okay, which tells us we have to be on a closed interval. So there's no guarantee that there's both a minimum and a maximum. Now, when I take a look at this, I notice right here is an absolute maximum. Does it have a minimum though? No. Okay, these are both open dots. There is no minimum. If I pick a point here and say this is the lowest point on the graph, you could always pick another one just underneath it before we get to that open dot, right? Because points are infinitely small, right? So we can keep getting closer and closer to that forever, right? So there is no minimum. How about this one? Does this meet the criteria of the extreme value theorem? No. It is on a closed interval, but it's not continuous. There's an open dot right here. That means we're not guaranteed that there's a maximum and a minimum. Now here is the absolute min. Here is a relative min. But there is no maximum. See, I tried to draw this at the highest, put a hole at where the highest spot that the function reaches, but we aren't guaranteed that there's a maximum. How about this one? Doesn't meet the criteria of the extreme value theorem. This is not on a closed interval. I do not have a maximum or a minimum anywhere in this graph. If I pick a point on the graph, you can always pick one higher, and then I can pick one higher, and then you can pick one higher. We can play that game forever, right? Okay, so important term for us is a critical number. Okay, as we find extrema, and you guys will probably catch on to this pretty quickly, critical numbers are really important. That's why they're called critical. So let f be defined at c. All right, so we have a function f. It's defined. There has to be a point there. If the x value is c, it has a y value. It is defined. If f prime of c equals 0, okay, so if the derivative of f at c equals 0, or f is not differentiable at c, then c is a critical number. Okay, so what does it mean? There's an or here, so there's two pieces to this. If this or that. So let's talk about if f prime of c equals 0. Okay. What would that look like? We're saying where the derivative equals 0. And there's been lots of times where I've asked you to find the slope of a tangent line. That's what derivatives do, right? And I've asked you things like find the value of x where this function has a horizontal tangent line. We know that the derivative gives slope. And if the slope is 0, okay, that means the tangent line is horizontal. So it would look something maybe like that. Here's our function f. Here is c, and f prime of c right there equals 0. The slope there is 0. And hopefully already you're making a connection. We're talking about extrema, and take a look at f prime of c equals 0. What do we have here? In this case, we have a maximum, don't we? Okay. Now, it's not the only way that f prime of c could equal 0. If I were to sketch another graph, like this, where here's c, and we look at f prime of c, right there, f prime of c equals 0. Okay. However, this is not an extrema, so we're going to make a few connections here. Just because there's a critical number doesn't mean there's an extrema, but they're very important in helping us find them. All right, so that's this part. Or if f is not differentiable. And what does it mean for a function to be not differentiable at a point? It means there is no slope of that tangent line, and that can happen a couple different ways. You may recall, okay, that we talked about sharp turns as not being differentiable. Right here, okay, f is not differentiable at x equals c, right? There's all these different slopes of tangent lines that we could draw. It's not differentiable. But again, notice it ends up being a maximum. in this graph. It could be a minimum if I flip that v upside down. What's the other scenario? Well, if it's not differentiable, it doesn't mean, it means there's not a slope. So that could look something like this, okay, where the slope at our point ends up being perfectly vertical. That's undefined, right? So if f prime is undefined at C, it's not differentiable. Okay, we end up with a vertical tangent line. Now, do we have an extrema there? No, we don't. Okay. But okay, we are going to say Fermat's theorem here. If f has a minimum or maximum, relative minimum or maximum at x equals c, then c is a critical number, right? So, okay, could you draw a function that has a maximum or a minimum at c where c isn't a critical number by our definition? No, like no matter how I draw it, there we go. Okay, I drew something that has a minimum. Is this value a critical number? Yeah, the slope is 0. That has a minimum right there. Is it a critical number? Yes. Why? Because f prime is not defined at c, right? There's just no way for me to draw a function that has a minimum or maximum without that maximum or minimum happening at a critical number. Okay? I'll make one other comment here because I'm just thinking back to these graphs. Okay? Notice there's a maximum. Is it a critical number? Yes. There's a minimum here. Is this a critical number? No. Well, it depends on who you're talking on, how you define. If it's a closed interval, the endpoint might be an extrema. Okay, so endpoints would be grouped in here. And that's why when we take a look at my guidelines for finding extrema, okay, what we do is we find the critical numbers and we evaluate the critical numbers. We find their y values. But then we also have to look at the endpoints and look at the y values of the endpoints. All right, so find the critical numbers, okay, where the derivative equals 0 or it's not differentiable. We then evaluate. We find the y value at those critical numbers. We then look at the endpoints and their y values, and then we compare them. And the least is going to be the minimum. The greatest is going to be a maximum. All right, so let's find the extrema here. F of x equals x squared plus 5 over 3, and we are on the closed interval -2 to 5. All right, so let's find our critical numbers. To find critical numbers, we differentiate. Before we do that, I'm going to rewrite this as 1/3 times x squared plus 5 to make differentiating a little bit easier. So our derivative is 1/3 times 2x. Critical numbers happen where the derivative is equal to 0. So we're going to say 0 equals 2/3 x. So we get x equals 0 is a critical number. Is that the only critical number? Well, we also have to ask ourselves, is there any place where the derivative is undefined, where it's not differentiable? And when I take a look at this, there is no value that I can't put into the derivative. The derivative is defined at every value of x. The domain of 2/3 x is all real numbers, especially on the interval -2 to 5. So this is our only critical number. All right. So we have our critical number. Okay, we need to evaluate our function at the critical number. So I'm going to find f of 0. Put 0 in, I get 5/3. But we can't forget about the endpoints because this is a interval, a function on a closed interval. So we also have to evaluate at -2 and +5. So when we substitute -2 in, -2 squared is 4, plus 5 is 9, that's 3. F of 5, 30, divided by 3 is 10. So what do we notice about this? Okay. Well, as we compare these, and we think about this from left to right, and I wrote these out of order here, but it might be more imperative in the future to put these in order. I'll give it one more shot here. Oh, they got it. All right, they're in order, but there's a little gap, right? So by in order, I mean from smallest to largest x values. -2, the y value is 3. At 0, it's 5/3, and at 5, it's 10. So notice, it starts up at 3, and to get, as we go to x equals 0, it goes down to 5/3. This means 3 is starting above the function, right? If I'm sketching a graph of this, okay, at -2, it's up at 3. Okay, I'll just say 3 is right here. I'm not following the grid here, but it's at 3. But then when we get to 0, it's down to 5/3. And then over at x equals 5, it's all the way up to 10. So you can see this is a really bad graph. But you can see we can get a picture that this graph has to come down and then go up, something like that. Oh, this is a horrible graph. My apologies. But I think we can identify where the extrema are. At -2, this must be a what? Local or relative maximum. At 0, it is the lowest point on our graph. Okay, that is the absolute minimum, and at 5 is the absolute max. So we're going to say x equals -2 is a relative max. X equals 0 is an absolute minimum. X equals 5 is an absolute max. All right, so let me go to the graph here. What was it? X squared plus 5/3. Okay, there's that quadratic, but we were only graphing it from -2 to 5. And it looks like that. So it's much better than my sketch, right? So at -2, it was up there at 3. At 0, it was at 5/3, 1 2/3. And at 5, it's up at 10. Okay, so we were able to put those pieces together. But you know what? Here's something interesting, and I was going to do this problem, but since we're taking a look at it, you guys notice right away that this is a quadratic, right? Okay, and if I just don't do a closed interval, if I just take a look at a quadratic, where do we have extrema on a quadratic? We have them where the function has its vertex, right? We did this a lot in the past. You guys did this in pre-calc. Algebra 2, hey, find the maximum or minimum of a quadratic, you find the vertex. How do you find the vertex again? I'm going to jump ahead here. Find the vertex of any quadratic equation. Well, if you remember, okay, when we did this, we said, okay, we have something, well, let's take a look here. If we have a quadratic function, we know the vertex is always halfway between our x-intercepts. And we said with a quadratic, the x-intercepts are always -b plus or minus the square root of b squared minus 4ac over 2a. And I said, what's halfway between those two x-intercepts? So our vertex is, well, -b plus the square root of b squared minus 4ac over 2a plus -b minus the square root of b squared minus 4ac over 2a, all over 2, right? Halfway between 2 points is the average. Add them up and divide them by 2. And we said, okay, well, those have a common denominator, so when we add them together, the square roots are gone because this one's positive, this one's negative. It ends up being -b over 2a over 2, and when we simplify that, we get -b over 2a. Remember, that's where the vertex of any quadratic is. And that was our thinking. But now that we know calculus and we know that the vertex is going to be a minimum or maximum, there has to be a critical value. So it's got to be a point where the derivative equals 0. So it might be much easier for us to think about, if I have a quadratic ax squared plus bx plus c, where does the extrema happen? Well, when we differentiate and we take our derivative, what is it? 2ax plus b. And we know if it's going to have a minimum or maximum, it has to have a derivative equal to 0. Okay, since it's differentiable everywhere, there's not that piece. And we get this equation. We'll solve it. Subtract b, divide by 2a. Look how easy that is. That's a much easier way to come up with our formula for finding the vertex of a quadratic. X equals negative b over 2a. If we just say, let's take the derivative and set it equal to 0. All right, so I got a little bit off on that. But let's get back to our problem. All right, feel good about that. Let's go to the next one. All right, let's not do a quadratic. Let's do something a little more interesting. F of x equals x to the 2/3 minus 12, and we're on the closed interval negative 2 to 4. First step, find critical numbers. So again, we need to differentiate. 2/3 x to the negative 1/3 minus 0. Okay. So where is our derivative equal to 0? Well, that negative exponent really sends that down here. This is 2 over 3 times the cube root of x, right? So the negative moves it to the denominator, x to the 1/3 is the cube root of x. Where is this equal to 0? Well, fractions are only equal to 0 where the numerator equals 0. This never has a spot where the derivative equals 0. So there is no f prime of c equaling 0. However, are there any critical numbers where the function is not differentiable? Remember, okay, that if f is not differentiable, okay, we also have a critical number. And for it to not be differentiable, we have to ask, are there any values of x such that c is defined, that we can put it into the function, but we can't put it into the derivative. And when I look at the derivative, I notice f prime of 0 is undefined. Okay, but can I put 0 into my original function? Yeah, 0 to the 2/3 is defined, isn't it? Okay, minus 12. That's a point on our function. However, on our derivative, it's undefined. So that means x equals 0 is a critical value. Okay, it's a critical number. Okay. It's not differentiable at x equals 0, even though the point exists. Okay. Now, there will be times where you might be like, oh, the derivative is undefined at a certain x value, but when you look back at the original, it's not defined there either. So you got to make sure that it's really a point on this, right? If I put 0 in, I get negative 12, okay? But I can't put 0 into the derivative. So this is our only critical value, critical number. So now let's take the endpoints and our critical value and let's evaluate them. And let's put them in order. So negative 2, we need to evaluate at 0, and we need to evaluate at 4. All right, at negative 2, we're going to substitute in, okay, negative 2 to the 2/3 minus 12. Oops. I get about negative 10.4. When we put in 0, we get negative 12. When we put in 4, we get about negative 9.5. So what do we see here again? We see it starts at negative 10.4, goes down to negative 12, comes back up to negative 9.5. So what does that tell us about each of these x values when it comes to extrema? negative 10.4 down to negative 12, up to negative 9.5. Negative 12 is got to be the lowest point on the graph. So x equals 0 is an absolute minimum. Okay. Negative 10.4 and 9.5 are maximums. Okay, which one is the absolute maximum? This one is higher than that one. So x equals 4 is an absolute max, where negative 2 is a relative max. All right, we put those pieces together. Endpoints, critical value, it's not differentiable there. It ends up being the lowest point. Let's graph this one just to check our answer. There we go. And if I restrict the domain, double check what my endpoints, negative 2 and 4. There it is. A cute little bird flying away here. So, relative max, absolute min, absolute max. And we see the not differentiable by the sharp turn that we have there at x equals 0. All right, I think this is our last one. Yep, because we skipped ahead to do that. Last one, f of x equals x plus 27 over x squared on the interval 2 to 5. So find critical numbers first by differentiating. Derivative of x is 1. Derivative of 27x squared, that would be 27x to the negative second. So, right, bring the negative 2 down, makes it a minus 54, x to the negative third. So minus 54 over x cubed. Now let's set that equal to 0. I'm going to add 54 over x cubed. I'm going to multiply by x cubed on both sides. Take the cube root. Can I reduce that any? Yes, 27 is a perfect cube, and it goes into 54 twice. So this ends up being 2 cube roots of 2. This is where the derivative equals 0. Are there any points where the derivative is undefined? So I look at the derivative and say, yeah, the derivative is undefined at 0. Okay, but two things with that. 0 already is not in the domain of f, the original function. It's also not in the interval that I'm interested in. Okay? If f was undefined in this interval 2, 5, we wouldn't be meeting that extreme value theorem piece where it has to be a continuous function. So this is our only critical value. Let's put them in order. Okay, when we evaluate. So 2 cube roots of 2. And 5, and let's evaluate. All right, put in 2. 2 plus 27 over 2 squared, 8.75. So 2 cube roots of 2 plus 27 over 2 cube roots of 2 squared. I get it doesn't look right. Let's try this again here. I think I'm typing something in my calculator wrong here. All right, found where I made my mistake. This is 3 cube roots of 2, not 2 cube roots of 2. Cube root of 27 is 3, not 2. That's going to help things out. There we go. So it doesn't change that, but let's go to the next one here. So cube root of 2 is 3. There we go. So now we're going to take that plus 27 divided by that squared. Get about 5.67. And then when we plug in 5 plus 27 over 5 squared, 6.08. Now we kind of see a similar pattern here. X equals 2 is an absolute max. X equals 3 cube roots of 2 is an absolute min. X equals 5 is a relative min. And I'm sorry I didn't pick any examples that got much more interesting than this. It was always kind of this like swoop down and then come back up graph like we have right there. But we can have different things that happen, right? It can start low, come up high, come back down again. Lots of interesting things that can happen. I know all my examples kind of ended up with that same general come down, hit a minimum, go back up. But I think you should be able to figure that out by looking at the Y values. So that's our start on Extrema. Excited. We're going to learn a lot more, and we're going to add a lot more tools into helping us find Extrema as we move along. Thanks for watching. We'll see you next time.